Hello, ladies and gentlemen. I'm going to do a little video recap of some of this angular momentum content. First off, I'd like to apologize that the audio quality is going to be atrocious. I was planning on doing this video on my home computer. However, as soon as I got home this afternoon, the power went out. And I was hoping that it would turn back on, and it didn't. So I had to go back into work, and the only way I can record here is via iPad recording. Not ideal. But angular momentum. So we're talking about it. It's the analog for linear momentum. If an object is undergoing some sort of circular motion, whether it's a solid disk that is rotating about its axis, whether it's a rock on a stick undergoing circular motion, if it's got mass, it's got rotational inertia, and if it's got an omega, it's going to have angular momentum. We looked at this in terms of just identifying the quantities involved. So we got angular momentum L is equal to I times omega, just doing the rotational equivalence of both mass and velocity. And we pointed out that there's now really two variables that can change in a calculation of angular momentum. Whereas in linear momentum, it's really just the speed that would change. In angular momentum, it's speed and within the rotational inertia, because mass is pretty much constant, it's the radius or the distribution of the mass that can change. We looked at conservation of angular momentum from the standpoint that you could have a single object maintain a constant angular momentum if it were to alter those two variables. If it changed the radius, the distribution of mass, you could alter, sorry, my little scribbles start to look like M's there. You could alter the omega. But we could also have conservation of momentum if two things collided with each other. In order to solve that, we set up this problem here, where we have something like a ball of clay with mass m, and it's moving in a straight line, and it collides with a stick, or rod, that's motionless. Now, if this were a linear momentum problem, the rod would just go into motion, it would bounce off of the ball. But if it's clay and it sticks to it, and I've got a pivot point, then we're going to have what we like to call a sticky collision or a perfectly inelastic collision between the two objects. We set up over here that object A, the ball of clay, would have angular momentum upon it entering circular motion of I times omega. Because it's a point mass, the rotational inertia would be mr squared. The omega would be its tangential velocity, which was its linear velocity before impact, divided by the radius, and r cancels out, and we end up m times r times v. If we reposition that, the angular momentum of a point mass is just the linear momentum it had upon entering the circular motion multiplied by the radius. Pretty straightforward. So if we try to solve this problem of the ball of clay slamming into a stick that can then rotate, we would take the angular momentum of the ball beforehand, ball of clay, mrv, plus the angular momentum of the rod beforehand, which was nothing because it was not moving. Then, like we would do for a perfectly inelastic collision, which we used to say is ma plus mb multiplied by some final velocity. In this case, it's not the mass, it's the rotational inertia that matters. So we would do the I for the blob of clay and the I for the rod rotating about its end point. All that multiplied by the final omega. And when we go ahead and set that up, we can, as long as the masses are the same for both objects, which I set up here in this picture, we can get to a solution. We can solve it. I'd have m times v times r equals, let's see, that's m and a 1/3 m r squared, so that'd be 4/3 mr squared times the final omega. I would cancel out an m, one of the r's cancels out, and I can solve for omega as, let's see, a 3/4 v over r. Now, in this case, that's the original velocity VA. So we're going to end up with an omega that's really just 3/4 of the original omega that we had over here on the right side of the screen. So it's losing some of its original angular velocity, but it's mostly because a bulk of the mass is far out. Total mass of the system is 2m, but half of it is all the way at the end, and the other half is distributed evenly from the pivot all the way out to the end. So it's mostly all the way out there, so you're still going to maintain a lot of your angular velocity. Let's take a look at something that's a little bit more like a problem we've seen in pivot interactives and a couple of the other questions on AP practice. And that's where you have one disk that has no rotation. Say that this has omega equals 0, and this has omega not equal to 0. And what if they were to interact with each other? If I dropped the upper disk down and it were allowed to hit and slam into the lower disk and they would move together, what would happen to the velocity? The final velocity of the system should go down compared to the original velocity. If I go ahead and call this, let's call it mi, geez, come on, that's an omega. If I have the omega I, that's going to be greater than whatever the final omega is for the two things together. But let's go ahead and set it up as a problem with some numbers. Let's go ahead and call this, let's say it's 1 kilogram, and it's got, Gmail notification, get out of here. Let's say it's got a radius of 0.25 meters. And let's say this larger disk has a mass of 3 kilograms, and it has a radius of, I don't want to put a capital R there, let's get rid of that, a lowercase r of, well, it looks like it'll be about 0.5 meters. If I wanted to set this up as an angular momentum problem, let's call this objects A and B, I'd have the rotational or angular momentum of A plus the angular momentum of B initially is going to be equal to the I for A plus the I for B times some final omega F. This is going to be a sticky or perfectly inelastic interaction. And for I, for both of these, since they're solid disks, the I would be 1/2 m times r squared. That's kind of our go-to equation there. So for LA, the angular momentum of object A, I would have 1/2 its mass. I'm going to go ahead and just leave this as MA for right now, times its radius squared, call that RA. Let's put some subscripts in there. Let's make this official. There we go. Squared multiplied by its omega I plus 0 for B. I'm going to put some color in here to denote which is which. And that's going to be equal to the rotational inertias of the two together. So 1/2 MA times R A squared plus 1/2 times MB times RB squared, all times the omega F. We're just barely squeaking in on the side of the screen there. At this point, there's only so much you can do with simplification. When the numbers are actually given to you, you can solve it. I can go ahead and get rid of a half though. That's got a factor of 1/2 on it, and this side has a factor of half in both of the terms on the inside, so if I factor that out, it will go away. And so I'd have MA times R A squared times omega I, forgot the A there, would be equal to MA RA squared plus MB RB squared, RB, like RBQ sandwich, times omega F. And at this point, there's nothing I can do other than just actually solve for it. So let's go ahead and do that. Omega F would be equal to MA RA squared times omega I over MA RA squared plus MB times RB squared. All right, I think I got everything in there. Then I can plug in some numbers and get to a solution. What do I got? I got 3 times 0.5 squared times, I never gave it an omega I. Omega I equals 2. Why not? 2 radians per second. Can't go wrong with that. All divided by 3 times 0.5 squared plus 1 times 0.25 squared. Now, as we look at this, we have the numerator and the denominator share a term here, and this allows us to really say that, if that second mass that was dropped on top was insignificant, if it was really, really small, then the first term in the denominator would dominate, and it would just cancel out with the numerator. We just have the original is equal to the final for the omegas. But in this case, it's not insignificant. That 1 times 0.25 squared it's going to give us something. Let's see what it gets us there. So that'd be 3 times a quarter, so that would be 3 quarters times 2. I'm trying to do this out of the calculator. So a quarter times 3 would be, that's be another 3 quarters. 0.25 times 0.25 would be in, what is that, a 16th? Quarter would be 16th. Oh, why did I do this? So that'd be 12 sixteenths. So 13 sixteenths on the bottom. And we'd have 6 quarters over 13 sixteenths. That'd be a 4 for 24 thirteenths. As easy as that, right? I apologize, I don't have my calculator here ready to go. So let's see if that's correct. So 24 thirteenths will give me 1.846. Omega F equals 1.846 radians per second. Feels like there's a math error in there someplace. So, but that's okay. It's okay if there's a math error in the bottom because the process is flawless. It's all about that flawless process. If I were going to score this on an FRQ, I'd get points for recognizing the I value. I get points for recognizing its conservation of momentum. I get points for substituting in the correct ideas for the masses. And then all of this stuff down here would be worth a point. So you make a math mistake in there someplace, no big deal. But anyways, that's a little overview of how we can set up a couple of those problems and solve it. I'll try and get some more stuff posted, even though I don't know when my internet and my electricity's coming back. But hopefully I'll get it done soon.